of my presentation is NMR spectroscopy basic principles and applications. Of course, I'm not going to very deep on this basic principles because most of the books these things will cover. Rather, I will mostly concentrating on the topics which were never focused while reading NMR, and sometimes some textbooks will never cover, because since I am in this field from last 15 years, so I know what all the things textbooks will cover, what all the things which are important, actually we usually never pay attention. So in that sense, I will rather focus more on that one. So at the end of my talk, I will give some applications. So at the end of the day, you have an overview of what NMR can do. So with this, I will dedicate my talk to late Professor H.S. Atreya. He is one of my NMR guru during my stay at IISc. During that time, he only joined and we lost him so early. So he is one of the brilliant biomolecular NMR scientists. Most of the tricks of the trade in NMR I learned from him. So in loving memory, I will dedicate my talk to him. Yeah. Coming to outline, of course, this is the season of Nobel Prizes, and NMR has many Nobel Prizes. So I will go through that one. Then I will just give some general information. Then some basic principles. Then we'll see there are two types of NMR, solution NMR and solid state NMR. And you will see why we have separate bifurcation in NMR called solid state NMR. So most of my PhD work and current what I'm doing at CLR is concentrated on solid state NMR methodologies. And finally, I'll show some applications of NMR. So this is a general trend. When general perspective that what is NMR? NMR means usually we'll see that, say that, okay, it will give structural characterization and we will get to molecular fingerprint information for molecule. Actually, this is just a tip of the iceberg. So there is a lot of things NMR can do. So such as molecular diffusion in variety of system, polymer chain dynamics, we can study with NMR, and biologist's favorite tool, NMR, because you can use NMR as a tool to get structure and dynamic information of proteins. That's why biologists love NMR. Now, this is a recent concept called dynamic nuclear polarization. So here what people are doing, transferring this polarization from electron to the nucleus, so thereby enhancing the sensitivity. So this is the new technique nowadays currently trending. Then NMR also found application in energy materials, particularly in lithium-ion battery. I will discuss at the end of my talk around this aspect. And one of the celebrated application of NMR to the mankind is magnetic resonance imaging. I will also spend some time explaining this concept. Then NMR is also used for quantum computation. And also NMR is also used in food processing as well as in medical field as well as in pharmaceutical field to study metabolites. So this field of NMR is known as metabolomics, where we assess different metabolites, try to get biomarkers, understand the biomarkers for disease in case of medicine, whereas in other field, same thing we can apply for food processing so that we can get the quality control. Having said that, now first we'll see some of the Nobel Prizes in NMR. So Otto Stern, first he gave the discovery of magnetic moment of the proton. So that is the basis for NMR actually. Then Isidore Rabi first observed this nuclear magnetic resonance phenomenon in molecular beam. And his method further improved by these two physicists, Felix Bloch and Edward M. Purcell, independently and simultaneously at the same time. And they observed this NMR phenomenon in bulk material. So NMR is originally by physicists. Later it moved to chemists. They use as this tool. And Richard Hens, he revolutionized this modern day NMR spectrometer by bringing Fourier Transform into NMR. So thereby we can speed up the measurement time. And also he brought multi-dimensional NMR technique. So here he is the one responsible for current modern day NMR spectrometer revolution. Next, Kurt Utrich used NMR as a tool to solve the structures of variety of proteins. That's why biologists love NMR. And finally, these two gentlemen showed that NMR can use for imaging capabilities. That's why we see in hospital MRI machines. Of course, like all of the spectroscopy tool, NMR has merits and demerits. If you see the merits, of course, it's a non-invasive technique, non-destructive, and it's very selective. Depend on which type of nuclei you want, that information you can get it, and it's a quantitative information. We'll get it at the end of the day. To list some disadvantages, of course, expertise is required. If you have a complex molecule and if you want to design some special experiments, of course, you need some expertise. And it is an insensitive technique. Among all the spectroscopic technique, if you see, NMR is a least sensitive technique. I will come to this point later. And also, NMR is one of the expensive spectrometer to maintain. I will also go through this one in a couple of slides. And also, automation is still challenging in solid state NMR, whereas in solution NMR, now most of the experiments you can do in automatic fashion. So you can reduce manpower, everything is automated, but still solid state NMR things are improving. So this is the NMR systematic schematic. That means if you enter NMR lab, this is what you see. So what we have a magnet. So these are all superconducting magnets. And we have electronics and we have data station. So what we have inside this magnet? So these are superconducting magnet. I will come to that later. It will generate very high magnetic field. So in NMR field, we always tell in terms of Tesla. And if you remember, in your laboratory, you have some bar magnets, and the strength of that bar magnet is always in milligauss. And Tesla is always a huge quantity. That means 10,000 Gauss is equal to 1 Tesla. So Tesla is a huge quantity. We never experience in our day-to-day life. So superconducting magnets are responsible to create such a high magnetic field. So we always deals with Tesla here. Okay, so we have here inside the magnetic field is a NMR probe, where we put our sample. Here NMR coil will be there inside the magnet, and it is connected to this console. So this console are electronics, nothing but it will transmit RF signal to excite this nuclei in the sample, and the same NMR coil will do two jobs. First, it will act as a transmitter by applying very high RF power. After applying the excite the nuclei by applying RF power, then same coil will detect tiny nuclei signal, which is in the range of microvolts. So it will do two jobs at a time, and that's why we always have a small unit always near the magnet. It is known as a preamplifier. So his job is to immediately amplify this tiny nuclei signal, because that should not lose in this RF in electronic noise. That's why we have a smaller unit near to the magnet. Then once we amplify this nuclei signal, then it will again send back to the console electronics, where we further amplify, where we do digitize the signal, and will finally process here. If you give a human body analogy, I can say this is your human body, and this data processing, everything, it controls this one. So that's why I will tell this is a brain and this is your heart. Okay. Now, if you see the cross section of magnet, what magnet contains? See, this is your sample will sit here, and it is surrounded by your NMR probe. And in the probe, your sample will sit. And this probe is surrounded by shim coils. I will come to that later. So shim coil is nothing but to adjust the magnetic field, to make a homogeneous magnetic field in the sample volume. And now we have superconducting magnets. So superconducting is a very low temperature phenomena. So particularly, usually we use niobium titanium alloy to create superconducting coils. And these become superconductor only at a temperature of 10 Kelvin. So naturally, to go to that temperature, we need liquid helium, because liquid helium boiling temperature is 4.2 Kelvin. So this superconducting coil is immersed in liquid helium bath. Then we have a vacuum, and further we have a liquid nitrogen bath. Then after that, we have a closure of this magnet. So I can say within a 1.5 feet, you have a temperature gradient from room temperature to almost near to absolute zero, 4 Kelvin. So that's why as we go for a higher and higher magnetic field, your cost also increases. It will rise exponentially. Because, so this is a recently, last week we refilled helium to our magnet. So this is a solid state NMR magnet, 400 megahertz. And you can see here one tiny box. This is nothing but preamplifier to amplify the tiny nuclear signal in the probe. So this magnet will.
We have in the computer science lab.
So this magnet will consume almost 100 liters of liquid helium, and in a year we have to fill twice. And liquid helium is not a cheap commodity. Liquid helium, 1 liter of liquid helium will cost 2,500 rupees. So now you just calculate the cost. And every week we have to fill liquid nitrogen. So it will consume around, this magnet is consume around 3,000 liters of liquid nitrogen in a year. So liquid nitrogen, of course, is a cheap commodity, cheaper than 1 liter of milk. So we are getting 1 liter of liquid nitrogen for the price of around 30 to 35 rupees. Now it requires 3,000 liters of that one. You calculate again. So maintaining NMR is not an easy task. So that's why we usually call NMR magnets as white elephants. Okay. Now there is a breaking news. Actually, recently, Brooker, which is pioneer in developing NMR magnets, so now we are going to the highest magnetic field. This is the one of the highest magnetic field we achieved with the 28 Tesla. That means now resonance frequency of proton, we usually in NMR talks in terms of megahertz. Now we are going in the gigahertz range. So that is possible because of so much research is going on in the development of high field magnets. Okay. So this is the first NMR spectrum of ethanol. Of course, one of the Indian was involved in recording the first ethanol spectrum, Professor Dharmati from TFR. And in the current magnet, if you do the ethanol spectrum, so this is the resolution we'll get because of high magnetic field. Okay, now coming to the physics of NMR. Yes, spectroscopy is nothing but interaction between the materials and the electromagnetic radiation, and nuclei, according to quantum mechanics, which possesses nuclei quantum number, it is characterized by, and in NMR we always deal with spin quantum number. Those nuclei with spin quantum number greater than 0 are only the NMR active. That means 12 carbon, 16 O, they are all I is equal to 0 and they are not NMR active. And here, this nuclei will possess magnetic moment. That means we can consider all nuclei like a tiny magnets. Now what happens? Of course, quantum mechanics tells that spin states of the nucleus are quantized. So they follow this rule. I think you all people know about this one. And in NMR, we'll talk, for example, we'll take a simple example. Hydrogen. In NMR, we'll never call hydrogen. We always call proton. Because it has a single proton, we always call proton NMR. So when I tell proton, you should understand that I'm talking about hydrogen. So now, if I take sample which contains protons, in the absence of magnetic field, they will randomly orient. So net magnetization is 0. The moment I put that sample in the magnetic field, there is a splitting of energy levels. This is characterized by this quantum mechanics rule, and this splitting we know that it is known as a Zeeman splitting. Now what happens? Now, according to quantum mechanical energy level diagram, some nuclei will orient with respect to the field and some orient anti-parallel to the field. So now, in NMR, we know that there are some excess nuclei will orient with respect to the field. So now we apply electromagnetic radiation, which equal to separation between these two energy levels, which usually in NMR falls in the range of radio frequency. That's why we use the radio frequencies. So that is known as the Larmor frequency of that particular nuclei to excite. Now, if you want to know the population of spins occupying lower energy state and higher energy state, now our friend Boltzmann come into picture. In Boltzmann distribution, if you wrote this formula and for a proton at 400 megahertz in the field of 9.5 Tesla, if we calculate number of population in the lower energy and higher energy state, we found that in a million, just 64 spins will be excess in alpha state. Alpha state means where the nuclei align with respect to the field. So that's why NMR is the least sensitive technique. That's why there is always mad rush to get higher and higher field, because as you go for higher and higher field, your population strength of the population difference increases. Thereby, you will have more number of spins to excite. Thereby, you can increase the sensitivity of the experiment. But problem is again cost will increase. Yes. Now, if you see this electromagnetic spectrum, we always lies in this range, that is radio frequency range, and each nuclei will resonate at different frequency. That is characterized by this fellow. This is known as a gyromagnetic ratio. So this will tell which nuclei will come at what frequency. So now you can see here proton in a 9.4 Tesla of machine, it will resonate at 400 megahertz. That's why we usually, our NMR machines, we represent in terms of Larmor frequency of protons. So if proton will come at 400 megahertz, whereas carbon will come at 100 megahertz, always 1/4 of that one. Whereas 15 and nitrogen will come at 40 megahertz, almost 1/10 of proton. Now, it is like your radio. In radio, you have different stations. So if you want to tune for that particular station, you have to tune and match particular frequency. So likewise in NMR, if you want to see proton, you have to tune for that particular frequency. Then only you will see the proton. Even though if in your system, you have a proton, carbon, or whatever, all the nuclei, at a time, you can see only one nuclei at a time because we have to tune and match that particular frequency. Then only we'll see that particular thing. If you are tune and match for the proton, we'll see information of only proton. Even if it is let's say phosphorus is there, carbon is there, that will not say because we are not tuning and match for that frequency. It is like radio you have to consider. Now, there is one more important concept in NMR. This is known as the abundance. So what it tells? So when you talk about protons are 100% abundance. That means if I take 100 atoms in my hand, in that all the 100 atoms will contribute to my NMR signal. Whereas in the case of carbon, if I take 100 atoms, in that only 1% will only contribute. And that is become worst in the case of nitrogen, only 0.37. So where it reflects, when you record NMR spectrum, if you record a proton NMR spectrum, since all atoms are 100% abundance, this is by nature. So you cannot alter it. Of course, you can do artificial synthesis, that's an expensive process. But if you take any system, it is like that. Okay. So if you record a proton spectrum, you immediately get the signal because it has a high abundance. Whereas for carbon, if you record a spectrum for 8 scan and for the same number of time, will not get that good resolution as well as sensitivity because it is low abundance, because number of contributing for that signal is less. So we have to go for higher and higher scans. So that's the problem for low gamma nuclei. So now this is the classical representation of the same NMR system. Now this everything is characterized by Bloch's equations. So this is not a right time to deal with the Bloch's equation. This will be there in textbook. Please go through that one. So what will represent, as we know that we have excess spins at the lower energy state that will orient with respect to the magnetic field. So the net population in my system, I have some net magnetization that is usually represented as mz or m0. So now I can manipulate this spin in NMR. So for that, what we'll do, so in NMR, we always consider field direction in the z direction. So our magnetization right now in z direction. So if we apply one RF pulse to excite this nuclei in a perpendicular direction, we can nutate this magnetization. So this is nothing but for those MSc students, this is nothing but perturbation to the system. Your quantum mechanics perturbation theory come into picture. If you wrote an energy expression for this system, that's visually represented as a Hamiltonian. So we have Zeeman Hamiltonian where spin interact with the magnetic field, and we perturb the system by applying a small RF field by RF. So now we can manipulate the spins by applying a certain RF of certain duration. That's why in NMR we always call pulse. We apply RF for certain duration. So this duration, we can manipulate the angle. That means if you want the spins to bring 90 degree, we have to give for apply for certain duration. If you apply for little double the time, then it will become 180 degree pulse. Then your magnetization will come like this. So that is in my control. Okay, so at the end of the day, I can flip the magnetization by any arbitrary number of degrees. Now comes Fourier excitation. So why this Fourier transform is revolutionized? Because Fourier transform is a mathematical operator. And what it does, it will decompose the signal into its constituent frequency. That means Fourier transform will transform time domain signal into frequency domain. Okay, now what it says, if we apply a square radio frequency pulse of finite duration, it is equivalent to applying a large series of few frequencies. What it means? That means if you apply a radio frequency of certain duration in a square shape, then we can excite all the frequencies simultaneously at one shot. Why this revolutionized? Because in earlier days, before Fourier transform, people used to use continuous wave NMR. That means either they have to fix the field, vary the frequency. Otherwise, they have to fix the frequency, vary the field, and tune and match for all the particular frequency. That was a laborious process and time consuming. So when Fourier transform Richard Nernst bring into the NMR, so in one shot, we can excite all the nuclei simultaneously. That's why it's speed of the measurement time. That's why it's a revolutionary concept. Now, what will happen once we excite the magnetization? That means from ground state to excited state. So in this picture, that means we are bringing the magnetization from Z to X or Y direction by applying RF in a perpendicular direction. Now, this magnetization will not stay forever here only. It will precess at different frequency. So this precessive magnetization induces current in a receiver. In NMR, we always assume our receiver coil is in X or Y direction. And it will give NMR signal. So this is your NMR signal that we call in NMR as FID. That means free induction decay. It will not be continuous. It will, as a function of time, it will decay. Now, if you Fourier transform it, this is a time domain data. If you Fourier transform it, we'll get frequencies at discrete intervals. So that's the beauty of Fourier transform. You can imagine Fourier transform like a mathematical prism. Like prism, how white color it will distribute into 7 distinct color because of prism. So like that, the Fourier transform is a mathematical prism. It will convert time domain, same information into frequency domain. So then we can appreciate this spectrum because here different proton signal coming at different locations because of its electronic environment. That's what chemists are exploit and chemists love NMR. Now, what are NMR observables? In general, NMR expands yield following information. Chemical shift give the frequency of the signal. If you know the intensity and if you calculate area under the curve, it will give population of spins. Line shape will give information about inhomogeneity of the population. And there is a spin-spin coupling, that is two spins interacting via through bond. So that also influence that I will see in a couple of slides. So now, why NMR is so powerful? That's because of underlying spin interaction. That means there are two types of interaction. One is external and is internal. External, we already know. One is Zeeman field or applied magnetic field and the RF to disturb the system. And we have internal. This is specific to your nuclei. What type of nuclei are taking. So we have chemical shift. It will give frequencies. We have scalar or a J coupling. That means a through bond interaction between the spins. Of course, we have dipolar. Right now, I'm not talking in solution because the solution NMR, these things will averaged out. Quadrupolar also will get averaged out. I'm not discussing this. This is a complicated thing. Right now, I'm done discussing. So we'll just concentrate on these two parameters. So that's why this is the reason NMR is very powerful. All nuclei will not come at one particular frequency. They will come at different frequencies based on its electronic environment. That's why chemists love NMR. So this is the usually spectrum. Usually it will go from right to left. I'll not discuss much on this one because this will be available in your textbook. So usually we always represent shift in terms of one with respect to TMS. And we always represent this chemical shift in terms of parts per million. This is a normalized scale. Why? Because if you record a spectrum, let's say in 500 mega spectrometer or 800 mega spectrometer, if you plot the spectrum in terms of frequency, now frequencies are different. To have a uniform scale, that's why we have normalized scale by dividing this megahertz here. That's why ppm, whichever the spectrometer you do for the same sample, the number will remains the same. So there is no confusion. That's why we always represent in NMR scale in ppm. So what is the advantage as we go for higher and higher field? So your resolution increases because span of the usually proton will come in the range of 0 to 10 ppm. As you go for higher and higher magnetic field, your span will increases. That means your resolution will increases. So this is J coupling, that is two spins through bond interaction. It is mediated by bonding electrons. I'm not going through that one. What we know that J couplings will give splitting in your spectrum. By looking at a splitting, we can say who is my nearest neighbor. So this is always covers in a textbook. So I don't want to go through very detail this one. Right now we'll assume J coupling we know, and all the splitting pattern always follow Pascal triangle. So now this is important concept. Most of the time we'll never pay attention to this concept. NMR relaxation. It is one of the complicated concept in NMR. Of course, there are two processes occurs in NMR independently and simultaneously. One is we call T1 relaxation. That is known as a longitudinal relaxation, or sometimes we call spin lattice relaxation. So what it says. Now, once we excite the nuclei from lower energy state to a higher energy state, that means coming from Z to X direction. Now this magnetization not stay forever. After certain time, excited nuclei will come back to equilibrium. Okay, that is what it says. So the amount of time taken by the nuclei to come back to its equilibrium state is known as a T1 relaxation. So why it is important in NMR? So this will tell after one scan, after recording the NMR signal, how long I have to wait for the next scan. Okay, so that is very important while running the experiment, NMR experiment. And this is follow this exponential increasing curve, this phenomena. Now, yeah, this is a cartoon picture of that one. And also there is simultaneously one more process will happen, T2, that is known as transverse or spin-spin relaxation. What it says, once you excite the nuclei, of course, it will come to transverse plane. Now your signal will not stay forever. It will try to precess at different frequencies. So T2 says how long your signal will survive. That is the exponential decay patterns. So now these two processes in our experiment tell how long acquisition I have to give in my experiment for this any nuclei you want to see. And after observing the signal, how long I have to wait for the next scan. So these two processes are very important in NMR. Okay, usually we'll never put attention for this one. Okay, now why these are important? Because your line width of your signal in NMR is dependent on inverse of T2. That means, what it means, if your signal is decays faster, then you have broad lines. If your signal is stay forever, little longer, then you have a very narrow line. So this is the case we observe in solution state, NMR, whereas in solids we face this problem. Lines are broader, resolution is always a problem. So I will come to that point later. Second, if we plot T1 and T2 has a function of correlation time. Correlation time is average time taken by the molecule for one rotation. Now if you see, for small molecules, T1 and T2 are almost in similar range. But as we go for a bigger solids, or for bigger molecules, now we see that we have not a favorable situation. In case of solids, we have T1s are longer. That is not good because we have to wait for a longer time for the next scan. Second, T2s are shorter. So that is also not a good news because the lines will be broader because resolution will get affected. Since this is dependent on correlation time, if we know these two parameters, then we can tell about dynamics. So that's why NMR is powerful not only for structural characterization and also for dynamics because of relaxation. And this relaxation process responsible for getting MRI images. So I will tell you at the end of my lecture. So these two processes are exploited in MRI imaging. So now coming to 13C NMR spectroscopy, we know it has low abundance and it will give much weaker signal compared to proton. And also always when you see carbon, there is always influence of proton because they are abundant in nature. Their influence also come into picture because through J couplings. I will not go through much detail. Yes, we'll see one example. While we are recording the spectrum for carbon, we always want to decouple proton because proton will always try to talk. In NMR language, what we call this interaction in terms of we will tell that they are talking. Spins are not silent, they are talking. Carbon wants to talk with each other. Proton will talk to each other. Protons will talk to each other if they are very nearby. Okay, so that influence will come into picture. If you see carbon spectra, proton influence come into picture because of this splitting. This is due to J coupling. Now we cannot assign this properly because it's a confusion. Now, if you decouple, that means we are continuously, when we observe carbon, we are continuously applying power to the proton so that we saturate their energy level. So that for time being, when you observe carbon, we will not see the influence of proton. So now what will happen? We'll get a clean spectrum only from carbons. That's why for characterization of any organic molecule, because they're full of carbons will be there, then NMR is very powerful and you have to always decouple proton. So for chemists, those who are involved in synthesis, for them, NMR is always bread and butter, because after synthesis, their first job is to confirm their structure or confirm their synthesis through NMR. So these are the chemical chart for different molecules and where it comes, their frequencies. I'm not going through that one. Yeah, now this is an important concept, sample preparation. How much sample you have to take in NMR? In solution NMR, we usually take sample in sample tube. There are NMR special tubes. So here compound should dissolve in almost 500 or 600 microliters of deuterated solvent. Usually your compound should dissolve in any of the deuterated solvent. Usually in NMR we are using CDCl3, deuterated chloroform, or deuterated water, D2O, or DMSO, or acetone D6. There are many solvents are there. Your compound should properly dissolve. And finally, it should give crystal clear solution. And sample length also matter, because amount of sample sit inside the coil also matter. If you give very less sample, will have problem because of some edge effects will come into picture. If you give too much of sample also, that will also create problem. So we have to give perfect 4 centimeter depth of sample in NMR tube, because we'll face shimming problem. I'll come to that little later. Yes, here. Sorry. Now what happens? If our whole aim in NMR, we should have a homogeneous magnetic field across this sample value. If magnetic field is not homogeneous, then within the sample we'll get to different frequencies for different part of the nuclei which lies in the sample, because they expand different magnetic field. So that we don't want. We have to get different frequency based on molecular environment, not because of sample, not because of sample inhomogeneity. So that's why in NMR, along with the NMR coil, there are some shim coils are there, almost like 40 in different directions. There are shim coils. That means we are passing the current in those coils and we are adjusting the magnetic field. So finally, we should get very homogenized magnetic field across the sample volume, so that we should get only one line across the sample. And now any frequency will come, it is dependent on its molecular environment, not because of a sample inhomogeneity. Okay. Now coming to the main part, NMR is always parameter dependent. So we should know what are the parameters are important while running the NMR experiment. And now we'll see how to record an NMR spectrum. Nowadays what happened, most of the machines are atomized. It is like a black box. We don't know what is happening inside. Finally, we'll get spectrum. Sometimes we'll not get spectrum. We never understand why we didn't get spectrum. So as a spectroscopist, you should know some parameters which are very important to understand why we didn't get spectrum, or some parameters to adjust so that we'll get a good and neat spectrum. So in NMR, we always talk about pulse sequence. That means it is a blueprint and every detail of NMR experiment will embedded there. It may be pulses, it may be delays. For example, this is just simple 1D pulse sequence. What we have here, we have some RF pulse for finite duration. Thereby we excite the nuclei. Then we observe the nuclear signal. Then after that, we wait for certain time because we have a relaxation delay. That means once we excite nuclear to the higher energy state, we have to wait for certain time. It has to come to ground state. That we have to respect. That is the system dependent. Now one may ask, so I will not follow this one. I will immediately run my experiment for the next scan. Now what happens? Now we will not get signal because we should have excess population in lower energy state. If you are starting immediately, then there are no nuclei there in lower energy state to excite. So you will not get any spectrum. So you have to follow this time to get maximum amount of signal for your next scan. Okay. Now accordingly, in NMR, there are multi-dimensional sequences are there like 1D, 2D, 3D and all. So these are all pulse sequences are available, different pulse sequences. I'm just giving some example. Each pulse sequence of different duration has certain meaning, and these delays have certain meaning to get some particular information. So when you become NMR spectroscopic, you have to understand why these delays are there, why these delays are not there. So why these pulses are there at certain intervals. So that you have to learn. Then only you will understand why that experiment is working, why that experiment, or why this experiment is not working, because this is very much parameter dependent. So now, coming to that, why we need multi-dimensional NMR? For smaller molecules, okay, but if you go for a macromolecules like protein, it's a big molecule. And if you see for example, this is the lysosome, it's the enzyme. and proton spectra at 900 megahertz machine. That means very high field, but still we will not get resolution. So many signals are there. So how to assign this one? It is challenging. So then people thought, why can't we add one more dimension to our spectrum? So thereby we can achieve a resolution. So that's why 2D NMR concept came into picture. So this is also a contribution of Richard Ernst. So what we have? So basic building block is we have preparation period. So there we prepare the magnetization and excite the magnetization, and this magnetization evolve during this time period. Then we have some mixing period. So that means it can be a series of pulses or delays, has its own meaning. And finally, we'll record the spectrum. So for example, if you consider 3 pulse sequence here, so how 2D NMR will execute? First case, there is a T1 will be 0 in the first case. Then we'll record the spectrum. For the next step, in a little step, we'll increase this delay. As a function of that, we will keep on recording the spectrum for a different step. So each data will store in a form of matrix. So finally, when we acquire sufficient data as a function of this T1 period, so we will do double Fourier transform, then we'll get two-dimensional spectra. So like that, we can add one more dimension into also 3-dimension also possible. In protein NMR spectroscopy, people are doing 4-dimension or 3-dimension or 4-dimension experiment and all. But problem is, as you increase the dimension, your measurement time will increases. For a 3D experiment or 4D experiment, sometimes it will take days and weeks also. So that's the problem. So now we'll see, this is one of the well-known correlation spectroscopy known as the COSY. It will give homonuclear correlation between the protons which are connected. Let's see. So here we have 2 dimension where chemical shift is present. So diagonal peaks are not interesting because diagonal peaks give the same information what we'll get in 1D dimension NMR spectrum. But here more important are cross peak. So in this is a 2-pulse sequence. One pulse will excite and evolve, and this pulse is a mixing period and will observe. So why we are giving 2 delays, I will not going to discuss. So if you use this pulse sequence, you will get this information. So what information will get? We'll get through bond correlation. So usually we have coupling in NMR between HA and HB because they are 3 bonds far away. But we don't have coupling between HA and HC because it is it's almost like more than 3 bonds far away. We'll not see the correlation between them. So now if you see in your spectrum, A and B are correlated because they have a J coupling between them. B and C are correlated. So we have a correlation P. So this is the same information. It's a mirror image. It's a mirror image here. So you can see at one particular half of this spectrum. Similarly, here D and F are correlated. You can see here D and F are correlated. Similarly here, and F and E are correlated, and D and E are correlated, whereas C and D are not correlated. So by running just 2D spectrum, we'll get the backbone assignment. We can assign this molecule, who is my nearest neighbor, in one shot. So that's the advantage of 2D NMR. In one shot, we can assign this molecule. Whereas in 1D NMR, it's very difficult. You have to find the J coupling and all. But here it's crystal clear. So that is the advantage of 2-dimensional NMR. So similarly, we have variety of sequence for heteronuclear correlation like HSK, HMK, HMDC. I will not go through those details. And we have in 3-dimensional correlation. That means correlation between proton, carbon, and nitrogen. So 3-dimension also possible. So I'll stop here. So now I'll move to the solid state NMR part. Okay. So now before going to the solid state NMR part, we have to know the concept of isotropy and anisotropy. Okay. Now, imagine a situation like this: morning prayer session. All children are arranged in rows. Now, if you see this teacher, he can easily move along the rows rather across. So this is the situation we experience in solids, where molecular motion is restricted and the measured parameters are dependent on the direction. So that is known as anisotropy. In contrast to this one, I have this situation after the assembly, disperse. Now students are randomly scattered in all the directions. Now this teacher has a equal difficulty move in all the direction. This is the situation we face in solution. Their rapid random translation, rotation, and tumbling of molecules, due to which whatever the measurement parameters are there, they are independent of direction. So that's why we'll get isotropic information. So with that, now we'll see, to see the matter, of course, we have gas, liquid, and solid. In liquid, we usually deals with isotropic. In solution NMR. Of course, there are some anisotropic case like gels and all. I'm not going through that one. If you see solids, you have plenty of system to cover. In solids, there are anisotropic, there are ordered system, disordered system, and order contain crystals, fibrils, glasses, and Vereter systems are there. Now you can ask, so what is advanced? Same I can do in solution NMR. Of course, order system you can dissolve in your system, you can dissolve in neutralized solvent, you can do NMR. But problem is all the systems, the order system or disordered system are not soluble in all the solvents. There are some systems which are not soluble in any of the solvent. Then you want to do NMR. So then you have to go for solid state NMR. So that's the way you have to go. So now solid state had its own problem. One is anisotropy. So chemical shift anisotropy. What it means? Let's take a simple example. If you take a single crystal where all molecules have uniform orientation across one direction, based on the orientation of this single crystal with respect to the magnetic field, its resonance frequency changes. Now in solids, there are millions of crystallites will exist with different orientation. So all of them give different frequency. At the end, if you put solid, you'll get broad powder pattern. Of course, you have a lot of information, but how to extract that information, that is a challenge. So this is what the problem in solids. Lines are broadened. For example, glycine, it's a simple molecule. We have two carbons, C1 and C2. If you see the spectrum, you'll get a broad line. Whereas if you see the solution NMR for this one, you have a well narrow line. One is here around 42 ppm and one is at around 176 ppm. This is okay, simple system. If we have one more amino acid, tyrosine, here many carbons are there. Now look at it. All carbons has its own powder pattern at the end, or all will give big overlap of bunch. It is look like a hill. So of course there is plenty of information. Now how to extract it? That's the difficulty we face in solids. And we have to address that one. Adding fuel to the fire. So this dipolar coupling come into picture in solids. So this is through space interaction between two spins. That means even though spins are not bonded, they are separated by some distance in space. They will talk with each other. So that will come into picture in solids. Whereas this will be averaged out because of a random tumbling of molecule in solution. So but in solids it will come into picture. Problem? Yes. If you have a proton-proton at a distance of 1 angstrom, strength of this interaction is around 120 kilohertz. In the case of proton and carbon, if you see proton-proton J coupling in solution, it is just might be 5 to 10 hertz for some system. It will vary. But whereas we are talking now in terms of kilohertz, so this is a huge interaction, and it will give us the line broadening. So this is where the problem. Again, this will also contribute to line broadening in solids. So we have to deal with this one. But advantage of this particular dipolar coupling information, it is proportional to R cube, that is distance between two spins. If you have this information, then you can get geometrical information. So that's why solid state NMR is very powerful to get the geometry information of the atoms. So in my work, I usually deal with this interaction to get the geometry information in a liquid crystalline systems. If time persists, I will go through that one. Otherwise, we'll see what to do. Yeah. So now, if you see the relative magnitude of interaction for solids and solution, now we see we have a big static field. We have RF field in the range of kilohertz. We have chemical shifts. We have J coupling. But in solids, we usually ignore J coupling because of this fellow, because this fellow is in the range of kilohertz. Of course, we have solids, we have to deal with one more fellow, that is quadrupolar coupling. When you have a spin quantum number greater than half, right now I'm ignoring this one. If you have spin quantum number equal to half, then this quadrupolar coupling never come into picture. So now this is a general situation. In liquids, there is a rapid tumbling of molecule. We'll have isotropic information, lines are well resolved. Whereas in solids, motion is restricted. Now you have a inherent line broadening. Of course, narrow is beautiful. That's what liquid state NMR people will say. But solid state NMR people like me will say broad is informative. But problem is how to extract that information. That's a challenge. Now, our aim is to get in solid state NMR like this resolution, like liquid, how to deal with this broadness. So people are smart. People thought if you write an energy expression for this interaction, that is Hamiltonian, for this chemical shift and dipolar coupling, they found that this Hamiltonian has a dependence on this factor. So this is nothing but legendary second order polynomial. And if you make this factor 0, then that interaction will average out. Then this interaction is not there. Then we'll have well-resolved lines. Broadness is no more into picture. So now, when this term will become 0, when you substitute theta equal to 54.7, then people thought we put sample in the magnetic field at an angle of 54.7 with respect to the magnetic field and rapidly spin the sample so that all the crystallite orient in different direction. They have a uniform orientation when you spin the sample at an angle of 54.7. Of course, that's what we do in the solid state NMR. We call it as a magic angle spinning. That means we are rapidly spinning the sample. So what it does, all interaction terms with angular dependence will goes to 0. And what it does in a simple terminology, it's a nothing but space diagonal in a cube. That means magic angle spinning brings symmetry into the system. Okay, so and in solid state NMR, we never use sample tubes. We use rotors or spinners. We call this is made up of zirconium, where we fill the sample as it is. There is no solvent business here. We take the sample, we use pestle and mortar, grind the sample, finely powdered sample, put inside this one, and we close that rotor with the cap. And you can see this cap, there are fins. So to rapidly spin this sample, we need some dry gas, which will come and hit these fins and it will rotate. Now, of course, your doubt is now how fast we have to spin. So that now we have to answer. So before that, we'll see this glycine spectrum in static condition. I already showed it is very broad. Now, when we start spinning the sample in magnetic field, now we can see already narrow lines are coming to picture, and there are many lines. These are known as this is the one genuine line. This is known as, we call it as an isotropic line. These are all modulated line because of spinning speed. Now we have to spin very fast such that we have to overcome this line width. More than this line width, if you spin fast, then all the sidebands will go away. Finally, we have a neat, well-resolved spectrum. So we almost achieve like solution state spectrum in solid state by rapidly spinning the sample. Okay. Now, how much fast you have to spin the sample? So that is depend on your probe, what type of probe you have in your laboratory. So if you have a diameter of your rotor size is high, then your spinning speed will be low. As the size of the diameter of your rotor will decrease further, your spin speed will increase. So now 2 years back, we reached a spinning speed of 1 lakh kilohertz, 110 kilo. That means 1 lakh rotation per second. So such a high speed, when you spin the sample, whole sample artificially think that it is in isotropic environments. So that's how we will get well-resolved lines. So that is a technology improvement. In 2010, when I was in PhD, so that time maximum speed we can think of about 50 kilohertz, 50 to 67 kilohertz. Now 2 years back, people achieved 110 kilohertz, but still there is an improvement. They want to go around 150 kilohertz. So there is research is going on in that direction too. Okay. As I told you, I will come back to this picture later. Of course, now we have to deal with this picture now. Now in solids, I told we have two problems. One is very long T1s and very short T2s. Very short T2s, we already deal with magic angle spinning because your line widths are, your signal is short means the lines are broader. But due to magic angle spinning, your line widths are now narrow. That means T2s are increasing. That's a good news. We address this problem. Now we have to address this problem. So now solids, I already told, proton have very high dipolar coupling. So proton NMR in solids still is not routine in solids. There are some specialized technique, but people never use proton NMR in solids. In solid state, first experiment people will do only for carbon, for any organic molecule. Now, problem with the carbon, so it is a low abundance nuclei. Its T1s are very, very long compared to proton. Proton, even though it's highly abundant in nature, T1s are short. But unfortunately, because the dipolar couplings are so high, we cannot achieve the good resolution, even in the magic angle spinning. But carbon, we can achieve the magic angle spinning good resolution. But problem is it has a long T1. Now, how to address this problem? People thought, and this fellow carbon has very low abundance, whereas proton has 100 abundance. It is like this fellow is a poor fellow, whereas proton is a rich fellow. Why can't he borrow some magnetization from proton? Yes, that is possible. I'm not going through the theory of that one. So that sequence is known as cross polarization in solid state. What it does? So here we first excite proton, then we will apply some pulse. During that time, we'll match the energy levels of proton as well as carbon. So thereby we'll transfer the polarization from proton to carbon. So it is mediated by the dipolar coupling. He is a agent, communication agent between proton and carbon. So thereby we'll transfer the magnetization and we'll enhance the enhancement factor depend on Garamagnetic ratio. For carbon, enhancement factor is the theoretical enhancement factor is 4 times. If you do nitrogen, enhancement factor will be the 10 times because it depends on Garamagnetic ratio. Now what happens? Now we'll see this example. This sample, alanyl histidine, if you just excite carbon alone, so we can see that the relaxation delay of carbon is around 1 minute. For after every scan, you have to literally wait 1 minute for the next scan. And to get a good signal to noise ratio, you have to run almost like 7,000 scans. But moment if you do cross polarization pulse sequence by transferring polarization from proton to carbon, same sensitivity I can achieve in 256 seconds. That means within 4 minutes I can finish this experiment. Whereas if you do only carbon, you have to literally wait for 2 hours. So that's the advantage of cross polarization. So in solid state NMR, whenever you give the sample for analysis, first thing they will do cross polarization and mass. That means cross polarization magic angle spinning experiment. So we'll get hierarchical lines as well as sensitivity enhancement. So this is the bread and butter for solid state. Okay, this is the first sequence if you give for sample analysis in solid state, be it the carbon or nitrogen and whatever. So I will stop here for solid states. So these are the overall picture of solution NMR and solid state NMR. Now we'll go towards application. Okay, I'll take some 5 or 10 minutes here and then I'll finish. Okay, now we have arsenals of NMR because strength of NMR lies in its spin interaction. So as I already told, we have relaxation. From relaxation, we can get dynamic information. I'll come to this little later. Here in NMR, we also vary the magnetic field for certain intervals that is known as a gradient, linearly varying magnetic field. With that one, we can get diffusion information, molecular diffusion information, as well as imaging information. I will explain it in later slides. Of course, as I already told in my second slide that nowadays people are transferring, like CP, we are now transferring polarization from electron to nuclei. So advantage is that we'll get almost 1,000 times of sensitivity enhancement. So this is a new concept. It is a very old concept. That means it's almost 70 years back this concept was proposed, but it was realized just few years back, almost 10 years back. So this is a recent field. It's known as hyperpolarization. Of course, quadrupolar coupling will get bonding environment. I am not dealing this one today. As I already told you, through dipolar coupling, we can get the distance information as well as orientation information, and chemical shift will get the chemical structure information. That's why NMR is like a Swiss knife. It is a multifaceted tool. With this interaction, you can apply whichever field you want. That's why it is such a versatile technique. Any field you mention, you can find application of NMR. So we'll see some of the application here. So first we'll see polymorphism. So that's the application of solid state. Solid state NMR is very popular in the pharmaceutical industry because polymorphism means ability of solid material to exist in more than one crystal structure. So for example, if you see, this is a indomethacin. This is a well-known drug for reducing pain and inflammation. And it is known that it exists in crystal forms of different shapes. And depending on the shape, its properties are changing. So controlling the shape is very important. Now, in this example, there are three types of indomethacin compound are there. One is alpha form, gamma form, and amorphous form. And if you take these three samples and do analysis in solution state NMR, naturally you have to take this component, dissolve in CdCl3. If you do, all information got lost. You will get just isotropy information. You cannot identify all the three forms. Whereas in solid, there is no solvent business here. You are taking the sample as it is. You are not altering the physical state of the system. So we can clearly distinguish between amorphous, gamma form, as well as alpha form. That's why solid state NMR is very powerful in identifying the polymorphism, and particularly in pharmaceutical industry. Second example, see diffusion order spectroscopy. So NMR is also used to separate the different compounds in a mixture based on differing translation diffusion coefficient. So here I'm talking about rotational translational diffusion, not concentration diffusion. Okay. So now what we are doing in this experiment, for a certain period of time, this one G1, capital G1, we are applying linearly varying field during the experiment. So what it does, it will spatially label the nuclear spin because of this nuclear varying magnetic field. And if that nuclei have a molecular diffusion in the system, then during this period, so that is mapped during this period. Now what will happen, if there is a molecular diffusion for that particular nuclei, then corresponding signal will get attenuated. That means as a function of time, it will decay. But whereas if there is no molecular diffusion will occur for that any nuclei, then its signal remains constant. So that is what we are doing in, it is known as a DOSY, diffusion order spectroscopy. I will not go through this pulse sequence in more detail, okay? So what we are doing here as a function of this gradient strength, we are constantly increasing the strength of this gradient, and as a function of this capital delta, we are measuring the diffusion. We are measuring the movement of this nuclei, diffusion of this nuclei. And signal as a function of gradient strength, the signal intensity will decay. Now this intensity will plot as a function of this expression. From there we are extracting the diffusion coefficient. Now software smartly plots chemical shift as a function of diffusion. So that means based on diffusion coefficient, we can separate the two constituents in your mixture. So for example, we have three different mixtures in your system. So now it is separated based on diffusion coefficient. If you have a bigger molecule, of course it will diffuse slower. So it will come at low diffusion coefficient. As the molecular size decreases, it will diffuse faster. So it will, your diffusion constant will be more. So that will come at different level. So this is nothing but in NMR we call NMR chromatography. A mixture containing different molecule can be confirmed by dosing. In chromatography, in chemistry, they are doing the same thing. They separate the mixture using column. So similarly, we can do it in NMR in one experiment. Also, this found application in aggregation to study the diffusion of self-aggregated system. Host-guest formation, when binding of small guest molecule within the larger host, which will slower diffusion to understand the host-guest functionalities, and also in supramolecular chemistry for assessment of molecular size, because your diffusion coefficient is related to your hydrodynamic radius. So thereby you can estimate the molecular size. So that is given by Stokes-Einstein's equation. So diffusion is a very popular and very powerful technique in NMR. This is one of the application of NMR. And NMR also found application in battery research. Because now, current global trend, there is a push towards efficient carbon-free technologies, as well as portable electronics. There is a boom. So naturally, there is a high demand for batteries. So lithium ion is one of the popular batteries, energy system. And of course, we know it's a multi-component system where we have electrodes as well as electrolyte, where during charging and discharging process, lithium ion will move in this electrolyte. Now we know that usually they are using liquid electrolytes, but they are very volatile. And we have recent incidents of batteries catching fire. So now there is again a push towards safer electrolytes. Now people are thinking about solid electrolytes in a lithium ion battery. But problem is the amount of lithium conductivity what we are achieving in liquid electrolytes, that is cannot match with the solids because lithium movement will be restricted there. So now people are pumping money to get a safer electrolyte to understand the lithium dynamics in variety of materials. That's why NMR is powerful. They have a homemade probe. There they put lithium ion battery and monitor the real-time movement of lithium in NMR. So lithium also NMR active nuclei. So thereby we can understand the electrochemistry of this system. So that's why NMR is very popular in nowadays in battery research. Finally, I will conclude this talk with this MRI basic principles. So we know MRI is one of the NMR's best application to the mankind is magnetic resonance imaging. Of course, people scared with the word of nuclear because of nuclear bomb. They removed that word. They only retain magnetic resonance. Since we are getting imaging, it is termed as magnetic resonance imaging. So what are the basic principles? How we are taking the image from our body? We know that 80% of our body is made up of water. So water is nothing but hydrogens. So now in our routine NMR, we are using constant, let's say we have simple case of 2 nuclei and we are applying constant field. Now both these nuclei will experience same field, their frequencies are same. Now moment we are applying a linearly varying field like gradient, what I said earlier in the case of diffusion. Now resonance frequency of nuclei will change based on the position. So this is what known as a spatial encoding. That means we are encoding the spatial information. So now we can apply in any direction, not only in X direction. We can apply gradient in Y direction as well as Z direction. So naturally we have a 3-dimensional capabilities now. So we can get the image from 3 dimension. So that's what the principle behind imaging. So now we can select particular slice of interest in our body. That is by using appropriate RF pulse of certain bandwidth and using linearly varying gradient. So not only one slice, we can, by changing the center of the RF frequency, we can select many slices, region of interest in our body. That's what we're doing in MRI machines. And in MRI, unlike NMR, it is a horizontal magnet. In NMR, magnets are vertical. So your Z direction is vertical. But in MRI, because the human body has to move inside, so it is in horizontal. So now we consider Z direction around, Z direction along the horizontal direction. So accordingly, 3 planes we define. Plane perpendicular to the Z direction, we call it as axial or transverse. This is the MRI jargon. Then plane perpendicular to the X direction is known as a sagittal cross section, and plane perpendicular to the Y direction, that is known as the coronal section, cross section. So I recently did, we have an MRI probe in our lab, so where we usually do for material imaging. It's not for clinical MRI, but we have in same NMR magnet, we have a small MRI probe to put. So I think I recorded, 1 year back, lady finger imaging. So without cutting this lady finger, I can take the slice whichever direction I want. That's why it is a non-invasive technique. So I have a cross section of 3 cross-sectional view of this lady finger. So you can see this arrangement of seeds inside the lady finger. So similarly, we can use it for human body. Now, how we get this contrast? You can ask how we get this contrast. This is dark, this is brighter, this is dark. How we get this contrast? That's the next question we want to ask in MRI. Yes, thanks to relaxation phenomenon in NMR. So now, in the case of brain, we'll see now. So now we have in brain, we have fat we have white matter, we have gray matter, we have cerebrospinal fluid. For time being, we ignore these two components. We'll just concentrate on fat, and this we consider as a water, blue one. So now we can see that fat relaxes faster, whereas fluid or water takes longer time to relax in terms of T1. So T are known as a repetition time. Whereas in the case of T2 relaxation, fat decays faster and cerebral fluid takes longer time. So his signal is very longer, whereas this is a shorter signal. Fat. This is known as a T means echo time. I'm not explaining why it is echo time, but you have to consider right now. Now, people are using just these two concepts to get the contrast in MRI. So now, what will happen? For example, you have a tumor in your body, let's say in brain or any other part. Now, what will happen? Near tumor area, you have fat will be there, you have water, and they have a different relaxation time compared to normal tissue surrounding that tumor. So accordingly, you can get the contrast based on this T1 and T2 values. So what we are doing here in MRI, if you want to get T1 weighted image, they are keeping lower TR time and shorter TR time. So what it means? So if you keep a shorter TR time, so we can see that fat signal relaxes faster. We have more signal at the ground state now, whereas water signal will take longer time to come back to ground state for the next scan. Okay. Now, in the case of T2, if you see, if you give a shorter T2 period, now fat signal is still stronger than the fluid. Fluid things stay forever, but it is still lower than the photon. Now, if you see the image, contrast image on in a T1 weighted image, now if you see, this is the region of fat, it appears brighter. And this black region is actually belongs to water. Now, in the case of T2 weighted image, what they will do, they will keep this period longer and this also longer. Now, what is the advantage? Now, if you keep this period longer, both water as well as fat will come back to their equilibrium state, and we have signal from both of them. But now, if we keep this period longer, now you can see fat signals are already decayed, but water signals still there. Now, exploiting these two delays, now in T2 weighted image, we'll get brighter water signal appears from water region, whereas darker from fat region. It is exactly opposite to earlier image. Okay. Now, if you don't want dependence on T1 and T2, and you want only the signal from proton density alone in the region of interest, now for that you have to keep longer TR period and shorter TE period. What it means? Of course, longer TR, both signals will come to equilibrium. Now, if you keep shorter TR, both signals will be there from water as well as fat. So now we will get image, it is independent of T1 and T2. So this is the basic principle to get contrast in MRI image. Of course, there are plenty of sequences are there to improve on certain aspects and all. I'm not going. So this is a basic fundamental principle. This is a full NMR principle they are using in MRI imaging. So with this, I'll end my talk. So I'll just take another 2 slides to explaining our organization. So I belongs to CSIR. CSIR is established by the government of India in 1942. It's before independence. And it has a pan-India presence of network of almost 38 laboratories, because each laboratory has its own work, in the sense, starting from space physics, oceanography, aeronautics, instrumentation, like variety of field, each lab is focused. So for example, in Karnataka, we have 3 labs. One is NAL Bangalore, it is concentrated on aeronautics, and CPMAS, that is concentrated on IT, and we have one of the famous institute in CFTRI, it is concentrating on food technologies. Similarly, we have a leather research institute at Chennai. And we all know that CSI plays a noteworthy role in human resource development, particularly giving this JRF and SRF fellowship, as well as also conducting this NET exams. And coming to CLRA, of course, our institute is founded in the year of 1948. Now we are entering into In another 2 years, we are entering into 75th year. And main motto of our institute, basic and applied research in frontier disciplines of science, engineering, technology, in leather, leather products, leather chemicals, allied areas. There are core leather groups. They are working towards leather, and also we are helping towards leather, and also we are working in basic science too. And Gandhiji vision in the year of 1934 itself, we should have a leather institute in our country, because there is a general conception among people that for the sake of leather we are killing animals. So that is a wrong notion. I want to highlight here that leather is a byproduct of meat industry, and this is a waste. They will just dump that skin of the animal into waste only. So now it is a problem, because one is it will pollute, and also a lot of wealth we can generate. So that's where CSIR a role to create wealth from that waste. And it involves a lot of biology as well as chemistry. That's where the CLRA role is there. And we also have PhD programs under Academy of Scientific and Innovative Research, which is known as ACSIR. Earlier, we used to give degrees affiliated to universities. Now we are giving our own degree under this ACSIR scheme. Usually we have a call for in the month of June as well as in July, 2 semesters. It will start from August and also other from January. Yes, at the end of the day, this is our NMR facility. So we have 3 spectrometers in our lab. This is a solution state 500 megahertz NMR spectrometer, and this is almost 20-year-old machine. So this is a superconducting machine. We charged in the year of 2000, because the superconductivity, as long you are maintained in that way by periodically filling liquid helium and liquid nitrogen, it will maintain that persistence of current, because superconducting is nothing but zero resistance. That means once you flow the current, it will persist forever, as long as you are maintaining that superconductivity. So we charged this magnet 20 years back, still it is working. These are 7-year-old machines. This is Bruker 400 megahertz solution state NMR. So this is well atomized, because we can put 24 samples at a time. This is 400 megahertz solid state NMR that I am taking care of. This is not atomized. Everything is manual here. Everything manual here, yes. Now references, of course, there are plenty of references are available. I will urge those who are interested in NMR, please go through these principles and application of NMR spectroscopy given by late Professor H.S. Athreya in NPTEL portal. Actually, this is sponsored by Ministry of HRD. Not only for NMR, all other courses for the MSc level given by IIT professor and ISc professor. It is very useful. You can download the material. You can videos are available in YouTube. Kindly use not only for NMR, on other subjects. And also those who are interested in NMR, this is the best book in terms of those who want to take career as NMR, understanding of NMR spectroscopy. This is the one book we rarely find, in the sense that this book is meant for chemists as well as for physics. Chemists, usually they are always afraid of mathematics. And this book almost giving explanation in terms of mathematics step by step. He will never skip the step. He will solve all the steps. That is very rare to find in any book. But this is the book. I love this book. And this is one more book, Spin Dynamics, Basics of Nuclear Magnetic Resonance. He is one of the pioneers in this field, Malcolm Levitt. This is one of the best books in NMR. And also I refer some of the other books for general sake. And also this is one of the best books for in terms of any common man can read this book, MRI from Picture to Proton by Macrobi and all. And also this is a very specialized book, Solid-State NMR Spectroscopy by Melinda Dever. Finally, of course, when I was in EPC, there were no smartphones, of course, no selfies. Of course, I found some pictures which are all scanned. Sorry for the low resolution. So I miss all my friends. I am fortunate to have good lectures during my stay at PPC as well as good friends, because all of them have helped me to shape my career. I'm missing all of them. And this is, I think, in the second BSc, we participated in, I think, annual sport meet, and I think we got award. That's what I remember. I think, somewhere here. And this is our wonderful and very cherishing trip to Madikeri. I think we were in the top of Talakaveri, I guess. Yeah, I'm somewhere here. And this is our last day in third year of BSc, just before this exam holidays. And I'm standing here, I'm carrying this computer science record book. I think I took the printouts on last day of all the programs to make a record for the practical exams. Yes, thank you. At the end of the day, I want to thank you, all of you, for this opportunity. I hope I convinced what NMR can do. And if you get bored, kindly apologize. I'll take this opportunity to take any question from your side. Thank you.
Thank you, sir, for the informative and interesting session. Any intellectual gathering is incomplete without discussion. So it's now the time for question answer session. And I request the participants to type their questions in the chat box. I now request Dr. B. Lakshmish Rao and Ms. Chaitra to start the interaction session. Over to you, sir.
Thank you, Divya ma'am. It was indeed a very informative session. And here are some of the questions which we will be selecting from the chat box from the Google Meet as well as from YouTube. The first question is, can the gas state, can we use the samples in gas state, or is it only possible in the solids or liquid state for NMR?
No, gas state NMR is also there. But it is not so popular, but it is there. In all state of matter, you can do NMR, but mainly popular is in solids and liquids. Yeah, it is possible.
Okay, the second question is, can we do the NMR for thin films?
Yes, yes. Of course, any solid materials, if it is there, you can do the not only thin film, anything. But of course, I think if a thin film is not dissolving in any of the solvent, of course, you have to do for a solid NMR. But solid NMR problem is you need powder sample, because I already told you we take the sample in rotor and we have to spin the rotor. Okay, for example, in our lab we have 4 mm probe. So that means I can go maximum speed of 15 kilohertz. That means 50,000 rotations per second. So now sample has to be uniformly distributed in that rotor, because I have to spin it very fast. So now problem is, if you give me thin film, I cannot put inside the rotor. So now what is the way to do an NMR? Of course, what you have to do, you take one sharp knife, take that thin film and scratch it. When you do the scratching, you will get some dust. So that is more than enough to do solid state NMR. We cannot take thin film as such, because this is a practical problem, because we have to spin the sample very rapidly. So there's a sample homogeneity should maintain across that rotor. Yes, it's possible.
Okay, thank you. The next question is, for the detection of initial stage of tumor, NMR results is actually struggling. So what is the basic problem with that? For the detection of initial stage of tumor.
Yeah, I'm so sorry for that, but I'm not a medical expert for that. Okay, so I'm not a imaging expert. So I just gave some theory of that one. So I cannot comment on that one. So I think clinical MR expert only can comment on that one. It's too specific. Yeah, sorry for that.
Yeah, okay, the next question is, can we find the diffusion coefficient of different ions in the polymer matrix using an MR?
Yes, people are doing. Yes, it's possible.
And
that's why NMR is very powerful, not only in solution, also in polymer chain dynamics, and also ions will be there. I forgot to tell you, even there is a movement of lithium ions in the electrolyte in LIB batteries. There are also movement of ions you can monitor through diffusion. Yes.
Okay, thank you. And the next question is, can NMR spectroscopy distinguish COVID-19 because it can distinguish a tuberculosis patient?
Yes, but it is a laborious process. Now because our main aim is to detect faster. okay, in COVID, because we have a large number of people are getting affected. NMR can do, I'm not saying that it's not possible, but you cannot detect very quickly. It is like initial part of my slide, as far as my understanding goes, initial part of the slide, I talked about wine picture I gave, this wine glass, and there I told about metabonomics. That means NMR used in diagnosing diseases in certain patients, where what they will do, they'll take some control samples, those are not infected, and those are infected, their biofluids they will take, they will analyze each and every patient, then they will use this data, do some statistical analysis. Finally, at the end of the day, they will arrive at some biomarkers that will potential for identifying the disease. So this is not a one-day job. So this is like you have to do for a certain number of patients and also like what currently they are using RT-PCR. So that is a now golden standard. That means it will give the result very fast. But NMR can identify, but it is not so fast. It cannot give within a day. That's not possible.
Okay, the next question is whether nanopolymers can be studied by using NMR.
Of course. Yeah, it's possible. Variety of nanoparticles, there are reports of their NMR. NMR is powerful, yes.
It's nanopolymers, whether nanopolymer can be studied using NMR.
Of course, means if your material dissolves in solution, you can do solution NMR. If your material is not dissolving, if you want to do solids, you can study it, of course. But what information you want to study, that depends.
Okay, and the next question is what and all information we will get from liquid crystalline compounds from the solid state NMR?
Okay, so that is my area of research. I didn't present it. I thought that it is too much. If you allow me, I can just present. 2 slides are there.
Okay.
So shall I present or?
Sure, sir, sure.
I have just 2 slides. Okay, I will just present. I put it at the end of the thank you. Okay, I will start. So you can see, no, my slides?
Yes, we can see.
Okay, so yeah, so we know liquid crystal is a mesostate. That means it lies between highly ordered solids as well as in between liquids. So it possesses short range order, not like solids high range order, but also it possesses property of solution like flow characters. So that's why in liquid crystal we usually characterized in terms of orientation order parameter. So what it tells, it is a general conception, means solid, this order parameter is 1, whereas for liquid order parameter is 0. Is somewhere liquid crystal can have order parameter in between these 2 extremes. Okay, now what is liquid crystal? Liquid crystal is a substance can have more than 1 melting point. Okay, now depending on the arrangement of the molecules, so molecules in the liquid crystal phase can arrange in layers that we called in a liquid crystal language as a schematics, and some they are arranged in a random fashion. They are almost behaves like a liquid, so we call it as a least order that we called as a nematic. And one more important property of liquid crystal is molecule on an average uniformly oriented along one common axis, that we call it as a director. And this director, when we keep this sample in the magnetic field, and this director will orient with respect to the magnetic field. That's what we exploit in NMR. So now over the years, many of these compounds which show liquid crystalline property, which have more than 1 melting point. So this is for all synthetic challenges, all due to synthetic chemistry. Variety of compounds like the banana shape, lambda shape, cone shape, ring shape, which have certain properties. And one of the best application of liquid crystal is your display materials, because they show some birefringence, optical properties and all. Now, what we have done in our experiment. So this is a very old data. In 2014 we published. So we took 2 liquid crystals. So these are known as banana liquid crystal because it is in a banana shape like this. So what we are doing, so as I already told, in my research work, I use this dipolar coupling. That means this, let's say for example, here carbon is there, it is attached with proton. I will try to measure this CH interaction. Not only that one, this one, like this, all the carbons, it has some which has an interaction with the protons. That will try to measure using this sequence. This is known as a SLF sequence, that is separator local field. That means in one dimension we'll get the chemical shift, in other dimension we'll get the proton-carbon dipolar couplings. As I already told you, using this dipolar couplings, I can calculate back by fitting our values in this geometry. I can get orientation information as well as distance information. Using that, we calculated the order parameter for this molecule. That means what we proposed is that this ring, which is very much rigid, that's why it will have a very high order parameter of 0.68. Whereas side ring, phenyl ring, which has a less order, which has a order parameter 0.50. And from this ratio of order parameter, I can also calculate the bent angle between these two axes. That came around 20, around 25. Whereas in the case of thiophin substituted liquid crystal, we found that angle is around 55%. That is well within the accepted value. So using NMR, so I can get the molecular level information. I can talk about what is happening at this ring, this ring, this ring. So that is a molecular level information because we are dealing with nuclei. So we can get the molecular level information. Similarly, this is our recent work, last week only got published. So here we take one monomer, dimer, as well as trimer. So 3 wings we are attached to the centrophenyl ring. So this all shows the liquid crystalline property. I'm not going to detail on that one. Again, we've done a similar experiment where we extracted a dipolar coupling and we computed the order parameter. Of course, at the end of the day, we propose how this, what is the conformation of this structure in liquid crystalline phase with respect to magnetic field. So now we in liquid crystal language, all these series of 3 phenyl rings will consider as a core in liquid crystal, and this chains will consider as a spacer. Okay, I'm diagrammatically represented like this. So in the first case, this molecule will orient in this fashion in the magnetic field. This is a dynamic average. Okay, this is the snapshot of that molecule at that particular orientation. Whereas when you have this center ring flanked by 2 wings, now this will orient in this fashion. It will make center phenyl ring make some tilt with respect to the magnetic field, and these other side wings are oriented in this fashion. Because this you have to take into consideration of symmetry as well as space volume. How this you cannot spread your wings because how molecule will arrange, that also you have to take into consideration. Volume of the molecule, packing value. And also for the final ring, it is kind of lambda shape. That's a planar structure representation. But actually, what we proposed is that it is not like, it is like a chair conformation. So it will be perpendicular to the magnetic field where other chains will come at the bottom. So this is what we proposed here. And also we are working from last almost like 15 years in this field. So recently we wrote a review of variety of liquid crystalline system, what we assigned. We use 13C NMR as a tool to get this molecular level information. That is what my work actually. So I didn't include it because it will take too much of time. But since you asked question, I'm just presenting. Yes. So this information only what you get in liquid crystalline systems.
Yeah.
Yes.
Thanks a lot for the wonderful answer. And
Yes.
Last question, I think it will be: can LS coupling influence the spectroscopic readings? NMR.
LS couplings, what do you mean by LS coupling? I'm not able to get.
So it is the okay, it may be the very basic question, like which will be there in the syllabus, I guess. So it is the
No, can you say
LS and JJ couplings. So there are 2 types of couplings which we can usually observe. LS and JJ coupling, right?
Yeah, J coupling is between the spins. This
Yes.
LS coupling I didn't get. Means in what context they are talking. I don't know. I didn't understand this question. Sorry.
Okay.
So you just post me this. I'll just go through it. Okay.
Yeah,
present,
sure.
I'm not able to understand.
Sure, sir. And the last question is: solution NMR is preferable over solid NMR? So
Of course. So I usually tell, and sometimes students will come, sir, I need solid NMR. So first question I will always ask them whether your compound is dissolved in solution. Yes. then I will always suggest first you do solution NMR, because solution NMR is an isotropic system. It is very easy to analyze, whereas solid is not. Solid's problem is lines are inherently broadened, and I already told polymorphism come into picture. Now what will happen? Let's say in your molecular system, let's say hypothetically, let's say you have 10 carbons in your system. If you want to record carbon NMR, if you do solution NMR, you will get 10 for 10 carbon, 10 lines. Whereas if you do solid NMR for the same compound, now either you can expecting less number of lines because of broadening, some overlap. Sometimes you can also get double number of lines. That means 20 lines because of polymorphism. Because crystallite orientation have different orientation. That's why solid NMR is powerful in pharma industry because of polymorphism. So I always tell solution NMR is something like eating like this, where solid NMR is something eating like this. So first, if it is your compound dissolving in solution NMR, means first do solution NMR. If you're still interested to want to do some other information, then you come to solid NMR.
Okay, thank you. So I think the later questions will direct you to the speaker directly, so that he will answer. So that the participant will get the answer from the speaker directly. Okay, so that's the end of the question and